Yes. Yes. Very good morning to you all. So first of all, we will welcome Dr. Veerabhadra Reddy garu.
Yeah, good morning.
Today he's our expert today. So I think most of you are there. Sir, Sir Veerabhadra Reddy garu, sir, shall we start the session or shall we wait for
Yes,
some
sir.
time, sir?
I'm ready, sir. Shall I start?
Yeah. Oh, just 1 second, sir. 1 second.
If you want me to wait, I'll wait.
Yes, sir. Just another 2 minutes, sir. We have only few of them joined now. Let us wait for another couple of minutes, sir.
Okay, sir. No problem.
Right. Yes, welcome you all to this fourth day of the uh, FDP. Today, we have with us Dr. Veerabhadra Reddy garu. He's a scientist F at RCI Hyderabad. And to know about Dr. Veerabhadra Reddy garu, uh, Dr. Reddy garu is he has his MTech from IIT Guwahati and PhD and postdoctoral from IIT Hyderabad. His area of specialization is dynamic testing and structural analysis, and his research topic is vibroacoustic coupling of cylindrical shells with source identification. And Dr. Reddy has a very vast work profile involved in shock and vibration testing of aerospace systems, design and structural analysis of vibration and shock test fixtures for number of aerospace systems, involved in indigenous design and development of 500 kg payload pendulum, shock machine and 0.5-ton air-cooled and 4-ton water-cooled electrodynamic shakers. He is involved in design and development of uniaxial piezoelectric vibration sensor, and he's also involved in post-flight vibration data analysis of flight trails. So, with this rich research background, Dr. Reddy will be addressing us with his expert lecture, and hope this lecture will be useful for many of you, in particular, who are pursuing their PhD and their uh, uh, and showing interest in the research areas. So, over to Reddy garu, sir.
Thank you, sir. Thank you for
Right,
your nice introduction. I'm just
right.
sharing
Thank
my
you, sir.
slides.
Thank you, sir. Yes, sir.
Yeah. Good morning, one and all. Sir, is it visible to everybody, sir?
Yes, sir. Yes, sir.
Yeah.
Yes, sir.
I am going to speak for the next 1 hour on dynamic testing in aerospace and defense applications. As this faculty development program is basically on condition monitoring, I am going to dwell upon aerospace and defense systems, how we can identify failures, how we can correct them, what are the methods to identify failures, like what are the different tests we are proposing, or what otherwise worldwide what people are doing, and what are the equipments required for that, and with associated instrumentation, and brief into most of the things. So my plan of talk is segregated or planned like this, sir. I will be giving a brief introduction on different environments that aerospace and defense systems will be experiencing, and I will be focusing mainly on this aerospace and defense environments, and in particular with respect to dynamic environments. So I'll be briefly describing what are the dynamic tests and how to simulate them in laboratory, and what are the elements required to simulate them, and the brief of those elements or test equipments required to simulate these tests. And I will also dwell upon recent trends, particularly in vibration testing, because nowadays this vibration testing is almost inevitable for most of the sectors, including automobile, defense, aerospace, nuclear, bio, everything. And to do vibration testing, we need something called vibration and shock test fixtures, which are intermediate elements to transmit the energy. So how to design them and what are the brief guidelines, and overall, when we have a problem, we need to control that problem. So to control that, how to mitigate the failures, or how to reduce the unwanted vibration that is coming in the aerospace and defense systems. I will be giving brief failures and corrective actions taken by us. As it is sensitive to our organization, I will not be dwelling upon the names, and more critical things I will not explain, but preliminary which are available in the literature and other places I will be dwelling upon. And finally, when we do some measurements from the flights, or say you are measuring a flight data, like in condition monitoring you have a realistic real-time data, how to analyze them, how to specify them into real environments, or how to simulate, or how to understand that data, I will be dwelling upon with respect to vibration and shock. basically using some techniques called vibration response spectrum and shock response spectrum. So, so now basically this aerospace and defense systems, if you see, they are very critical systems. They house number of subsystems, means small units, and any one system malfunction is going to affect all the total system, which is very detrimental and very costly. See, for example, you will be hearing like a number of automobile manufacturers are recalling their equipments after some service. That is due to the failure modes. If we can identify such failures beforehand, we will be able to save a lot of money. For automobile, you can recall, but for aerospace like satellites or launch vehicles or say some other aircraft, you can't recall. It is going to be fatal. So all those probable environments have to be identified beforehand, and they have to be simulated, and all the subsystems which are going in these systems, or call this as a bigger systems, have to be tested for those environments. So they may be varying right from storage, transportation, and service environments. So these environments as are very critical, as they impose severe stress on the components, and like mechanical and thermal environments, and they cause serious failures. So to ensure reliable aerospace system, it is definitely necessary to simulate all the probable environments and subject the systems to environments and precipitate the failures. That's what I was telling beforehand. If we can precipitate the failures, we will be saving a lot of money. And then we also need to have a corrective action, how to overcome these failures or ruggedize them. So there are concepts like environmental stress screening, high accelerated life testing halt, high accelerated stress screening, which are very much used in different environment, different industries. But with respect to aerospace and defense, because the HAL task is very costly, we only use ESS, environmental stress screening, and that is how the failures are precipitated beforehand. So environments are generally for this category of aerospace and defense systems are categorized into two types: climatic and dynamic. Climatic, what we mean is the natural environments, which include like storage, deployment, and depending on the marine and mountainous conditions like high temperature, low temperature, thermal shock, uh, damp heat, and other things. But I'll be dwelling mostly on dynamic environments in this session, which is actually man-made or due to operational requirements. Like when you are handling, if you suddenly drop, how to overcome the failure, or what happens actually when you are transporting some critical system in some road, air, or rail transportation. The system is going to be subjected to different environments, and some vibration levels will come, and how to mitigate the vibration levels or how to protect the system from these levels. And also you will be seeing our roads conditions are very, you have different troughs or say different road breakers, and these also introduce some shock or what we call as bump. These also need to be simulated and tested. And apart from this, in actual realistic service environments, you may get number of other sources of vibration, shock, and acceleration. Acceleration, when we mean, is whenever object is taking a turn, you get an acceleration, that is centripetal acceleration or centrifugal, depending on the pseudo force, and that also needs to be simulated and tested. So all these environments need to be tested. So the why we are testing or we are simulating these environments and testing is due to ruggedize our systems and to check the functionality beforehand. As I said, defense and aerospace, the subsystems are very critical. So functionality of each subsystem under these environments, whatever it is going to experience, has to be checked before. So those environments will be simulated. For example, typical where we are going to get vibration, I'm listed here, like we get in transportation and flight, means actual launch. Shock again in handling and flight. Bump is due to transportation. Acceleration due to flight. Climatic condition can be both operation and storage. So I have listed here few environments which are called induced environments like this. Apart from vibration, shock, and bump, we also have something called acoustic vibration, that is due to the airflow. I'm not dwelling more because this acoustic vibration generally failures are very low, and I'll be dwelling mostly on vibration shock and bump, which are more profoundly found in our systems failures. Other environments for the natural are listed here. They range from thermal shock, that is whenever any aircraft goes from one altitude to another altitude in small time, we get thermal shock, and when some systems are exposed to outside solar sun, we get solar radiation, and due to the fungus and mold growth and many other operational or storage requirements are there. Where are these used? These are used in applications I have listed here, mostly aerospace, automobile, nuclear, heavy industries, electronics and appliances. And while simulating, there are different tests again. We call qualification test, acceptance test. The difference between them is qualification is verification for design. If the levels are high and we are trying to validate the design, we call it qualification test. And on a batch wise, we do this, or once we do this in lifetime. Acceptance tests are like we do it for every sample, like every 100% sample, 100 items you are going to buy, you are going to test it for 100 items and see that the function is verified in the given environments. These are all slightly relatively low levels compared to qualification. And to do all this, we need test facilities, test procedures, standards, and we also need some instrumentation systems like data acquisition, sensors, and associated fixtures. And we also need to have a lot of FE associated structural analysis team for doing this. So basically, dynamic testing, as I said, sir, I'll be dwelling upon vibration, shock, and there are something other shock also called pyrotechnic shock. This is due to some pyros or some shaped charges which actually explode during the operation, like balls, pyro balls. And apart from that, we have bump and acoustic test. And model analysis is usually done to know the natural frequencies, mode shapes. Even say for example Airbus, which a full vehicle Airbus will be subjected to model analysis and to know the different frequencies of its wings, fins and many other components to know whether any flutter is going to happen or so. This is also one kind of diagnostic test. So if we see generally worldwide or from our experience, we have put different environments and its ratio of failures. So we have seen most of the failures is due to thermal test and other tests due to vibration. So thermal is contributing to 40% of the failures that are seen in these industries, and vibration is attributed to 27% of the failures. So shock and is relatively less to 2%. So I'll be dwelling upon vibration and shock, sir, in the subsequent slides. And before going, I just wanted to say what is screening means. Generally, when we have a new design of any component, the component initially there are a lot of failures. That what we call as LE failure period. And what this curve is called Bhattacharya curve. This shows failure rate versus the time of its usage. After some time period, the failure gets stabilized and number of failures comes down, and then failures are only due to the random failure or fair use actually. And again at the fag end of its life of the component, you see failures increasing due to wear and tear and other issues. So if you see the cause of failure by the failure period initially, at the early period, it is basically due to the defective design. This is what we need to correct it. And so if we can remove this defective design by testing, so you will be ending up with random failures. It's a fair issue. So apart from that, it can also be due to defective manufacturing, defective material and unsuitable for environment. So most of the tests will remove these early failure periods, and once stabilized, so the mid failures or what we call random failure period is due to basically due to misuse or some fluctuation in environmental conditions. And the fag end of the life of the component is basically due to corrosion or fair wear and tear actually. So screening is often used in our aerospace industry to weed out these latent failures. That means initial failures actually. And it usually is a combination of high temperature, high and low temperature cycles along with the vibration actually. So now, as I said, I will be dwelling upon dynamic tests. So how to simulate this dynamic test? What are the dynamic tests and what are the equipments required? I'll be dwelling, sir. So for dynamic test, basically these are the four tests widely used in the aerospace and defense industry. One is vibration, then it is followed by shock, bump, and acceleration. As I said, vibration and shock are due to basically operation, or that is actual environment. Bump is the road transportation condition, and acceleration is again flight condition. So how we simulate each of these tests require different equipments, and what are the different equipments we need, how to use them, I'll be. So first let us see vibration. Sources of vibration in generally, apart from aerospace industry, what are the general source of vibration? Vibration is like to and fro motion. It is almost generated by whenever there is an imbalance forces, or when any force is exerted on system. See, in a general example, in IC engines, because of the combustion and rotation of automobile engines, or in road, if you see, if you are traveling in automobiles, because of the road irregularities you get. And in our actual aerospace or other industries, where you have turbines and other rockets, you get due to the propulsion systems, and also aerodynamic noise, actually there is turbulent noise. And the same acoustic energy excite at different points due to the aerodynamic flow. And apart from that, you can see even when you are riding on horse or somewhere doing jogging, many even our body gets excited. So but what happens is, in typical aerospace industry outputs, if you see during the liftoff, you get a shock or noise, and due to the propulsion, you get again vibration. Again, due to the aerodynamic noise, we get lot of vibrations, and due to the external surfaces, also get different vibrations. And if it is a liquid propulsion, you get even sloshing and other interaction like pogo oscillations. If you see the typical frequency ranges of these vibration ranges for like automobile industry, aerospace and defense, and railways. For aerospace industry, we need to typically excite up to 2000 hertz, because this is what is seen from the aerodynamic noise. And if it is automobile industry, even 500 hertz maximum frequency, I am talking about maximum frequency, 500 hertz of simulation is enough, up to 500. And if it is ship or other marine industry, because of its long bigger size, maximum frequency up to 33 hertz simulation is enough. But there may be some components which are even higher. Those subsystems, yes, we need to simulate at higher frequency, but as a whole system, we need to simulate up to 33 hertz. If you come to railways again are intermediate between aerospace and automobile. It is up to 1000 hertz. So what does the effect, what does the vibration do to different parts? Like I'm typically talking with respect to defense applications. In you have different electronic components which have different PCBs, different parts, different solderings. So due to this vibration, what basically we get in aerodynamic noise, what we call as random vibration, we get soldering issues or connector issues, or what we call as shorting of electrical parts. And due to bolt and other component, when assembly is there, we get component fatigue and also get loosened. And there are some, suppose elastomer seals and other things, due to this vibration they get deformed and they get wear, actually tear. And there are some relays and heavy components which actually during that vibration of short movement, the relay may operate though signal is not given, and then that cause some other issues to the operation, actually operation of the systems. So these effects, apart from that, if you can see in actual cracking and rupturing of some bonding of structures, or some line noise, or if there is a propellant grain and the boundary, there is a debonding, and they may even mechanical structures get loosened due to the screws, actually. To just have a feel of vibration, what it can do, what damage it can do. These are, I'm just going to explain. This is a Tacoma Narrows Bridge. We all know in 1940s, wind induced oscillation caused the collapse of the bridge. And similarly, Challenger in 1985, 7 members of crew as actually were lost due to the o-ring deformation due to the high vibrations and also temperatures. Similarly, we have flutter seen in number of aircrafts, and one of our say here non-sensitive, this is called ground system, which is called rugged PC, which again has failed due to the vibration. I'll just play one by one video, sir, for your understanding. This actually failed due to the torsional mode and bending mode coupling of the bridge, and also the This bridge actually did not have openings for the air to pass through, or what we call passage to pass through. So one day when the air velocity was high, the bridge collapsed actually. The entire bridge, only 7 to 8 months of its inception, it collapsed. Afterwards, one professor has done a basic hand calculation and shown that the bridge natural frequency, that is bending and the torsional modes coupled, and that's why it failed actually. So that they ultimately it failed actually. Similarly, this is what we call flutter. Flutter is whenever the external surfaces aero elastic interaction is there. Again, same, so bending and torsional modes coupled, we get unstable oscillations of the fin or this control surfaces, which aircraft will lose control actually. This is again one of our system. We can see we were giving a sine excitation from one frequency to another frequency. When the resonance of the structure came, it oscillated violently and it was about to fail before we intervened and stopped the test actually. You can see violent, this almost resonant. If you would not have stopped in another 1 second, it would have failed actually, it would have come out actually. So such manifestations of vibrations are resulting into resonances, and these need to be attenuated, and source of the problem has to be identified and corrected actually. So vibration not only poses disadvantages, it has some advantages, like we are able to hear each other due to the oscillations of the sound waves. It is also widely used in diagnostics of health monitoring and other conditioning. So condition monitoring applications are there. And we are also used to test now by imparting the vibration and see test the systems. And even we are often seeing road braking and other things, again that is due to vibration only. So some useful vibrations, like same way I have put here, in ultrasonic applications and concrete compactors, component feeders, and for road braking and other things, it is used widely. But however, there are disadvantages and advantages. We need to, yeah. Now, just as I was speaking about vibrations, so typically we experience two kind of vibration in aerospace industry. One is called sine vibration, one is called random vibration. Sine, what we mean is we have a single fixed frequency at a given instant of time, like say 20 hertz, 30 hertz, 40 hertz with some amplitude. And you can start from one frequency to another frequency, what we call sine sweep, move from one frequency to another frequency and excite the system. The typical specifications are there, like you can say 5G 20 hertz to 2000 hertz example. Now, to demonstrate a difference between random and sine, what is random? Random is like you have all frequencies excited at the same time. That means number of frequencies, like if you say take a band of 20 to 2000, all frequencies with some resolution are present at any instant of time. So where random is more dangerous compared to sine. See, for example, we are showing one experiment here in which one shaker is put on one simple plate, what we call simple metallic plates with say a 20 hertz and 30 hertz frequency are designed and kept. If I excite 20 hertz, only one of these will oscillate. If I excite 30 hertz, only one will oscillate. Means at 30 hertz, 20 hertz oscillation is less. At 20 hertz, 30 hertz oscillation is less. But if I do random vibrations at same 20 to 2000, both will oscillate and both will touch. So that is where multi-frequency excitation, that is where in 1940 Second World War they realized, until then it was only single axis vibration tests were done. Then they realized random vibration is required for this kind of multi-frequency excitation, and where components are very close by and where you don't have sufficient clearances. And this is definitely is going to be the case in aerospace systems, because systems have to be packed very close to each other and there will be very little space, or we call clearances between system to system. And basically where we do random is all our vibrations that we are experiencing in service is actually random vibration. So but to simulate this, we need complex systems and we need more power. Sine we use mostly for fatigue testing or diagnostic testing, but in actual disadvantage of this sine testing is it is not a realistic representation, and it causes failures which won't occur in service, and it hides multiple resonances. Like I was explaining, if you have a system which has multiple resonances closed by system, closed natural frequencies, or we call multi-degree of freedom systems which has more close natural frequencies, then sine may not excite all the modes simultaneously, whereas random vibration will excite, and that is the actual realistic environment. So in those cases, we need to use sine random vibration, and where you are using for other purposes, we can use sine vibration. And sine also is used in whenever there is rotating parts. Like for example, helicopter is there. Helicopter, you get both sine and random combined together. So we call it as sine and random vibration test because of the propulsion system or the blade propeller, we get a fixed sine tone, and due to the aerodynamic noise, we get a random vibration. So in those cases, we have to couple both sine and random. Likewise, there are cases where you get random and unrandom, like a broadband random coupled with narrowband random. That is like if you have a gun firing along with some motion of the helicopter or motion of the aircraft, jet aircraft, you have both simultaneously occurring. So whatever may be it, different combination of environments are possible, but basically the two are sine and random. So now how to simulate sine and random? Both are simulated on one equipment. Test specifications will be different. Now I'll be explaining them how we are simulating in laboratory and we are simulating. So to do this vibration test, we need three things basically. You need vibrator, what also sometimes referred as shaker, electrodynamic shaker or mechanical shaker or electrohydraulic shaker. And we also need a component, some system called power amplifier, and something called controller and accelerometer or instrumentation system or data queuing system. Apart from this, we also need vibration test specifications. Nowadays, for each industry, there are different test standards where one can follow the test standards initially if you don't have the measured data. But once measured data is available, you can frame the test specification from the measured data. I will be at the end of this lecture, I will be dwelling upon the test specification development, that is from the measured data. And other things what we need is item to be tested, or what we call as unit under test. So once we wanted a vibration test on a system, so we need a vibration test system, we need a test specification, and also the unit to be tested. A typical vibration testing philosophy I am highlighting here, what we call a shaker and some associated fixtures and other unit is here. So the unit which is going to be tested is sitting here. And now I was referring to power amplifier, that is this system, and controller. Now initially what happens, the vibration controller will generate, there is a test specification given to the vibration controller. We feed it and that spectrum is generated and sent to what is called as amplifier. This in the form of something called drive. This amplifier will give the required inputs to the shaker for its voltage and currents, and the shaker starts oscillating or moving. And the required spectrum, what is required or desired, is felt on the web section. This is again monitored closely, what we call as closed loop control, and it is compared with the input spectrum or input profile. And if there is any deviation, again the next cycle the error signal is sent, and this is how the closed control system works actually. In this so I'll be explaining about shaker and other associated components. So what is the principle of electrodynamic shaker? So what generally we are using is electrodynamic shakers. I will tell initially the history started with the mechanical shakers, followed by electrohydraulic, and then electrodynamic. I think it is, yeah, I'll just first see what is the difference between mechanical shaker, electrohydraulic, and electrodynamic. In initial days when 1940s, we had only single frequency, and also we were able to, because of the motor RPM, we were able to generate from say a band of 10 to 55 hertz only. Then the advancement of 1970s and 80s, electrohydraulic shakers came, which we were able to generate up to DC to 500 hertz. With advancement of electrodynamic shaker, we are now able to simulate between 5 to 2000 hertz. For small shakers, we can go even beyond 4000, 5000 also. The best shakers among the three is the electrohydraulic shakers, which are very good for simulation of random, sine, and many other advantages actually. Electrohydraulic shakers are nowadays preferred only for low frequency tests actually. Mechanical shakers are outdated. So now as the electrodynamic shakers are more predominant and they have wide variety of test capabilities, we will see what are the working principles. The working principle of electrodynamic shaker is it works on Fleming's left hand rule. That is a current carrying conductor placed in a magnetic field. You get force perpendicular to these two. That is magnetic field and current carrying conductor. So basically it is F given by Fleming's left hand rule. It is B cross actually a cross product of B cross IL actually. So B is the flux density, I is the current carried in the conductor and L is the length of the conductor. So different capacity of electrodynamic shakers are possible nowadays, right? Ranging from say small say 100 newtons or say 500 newtons to say tons, like we have say 16,000 kgf or say 1,60,000 newtons, we call is a 16 ton or 20 ton, like that. Again there are in within electrodynamic shakers there are different kinds of shakers. For very low range we have permanent magnet based shakers. In between range we have air cooled shakers, and very high force rating shakers we call as water cooled shakers. Apart from the basic shaker, we have another device called power amplifier. This purpose of the power amplifier is to provide power to the vibrator. Basically in the vibrator, what we call as a shaker, we have two things, armature and field coil. In the Fleming's left hand rule, we have F is equal to B cross IL. So B is the magnetic field flux density. It is produced by something called field coil, what we call as electric coil or field coil, which are electromagnetic coils actually. And I is the current which is carried by a conductor, which is what we call as armature. It is similar to motor. We have armature and field. Here also armature and field. So the purpose of the power amplifier is to pump the energy, that is both the DC power to the field and AC power to the armature, so that it oscillates in the shape that you want. The more force you want or more acceleration you want, you need more current actually. That is the basic design of the amplifier. So if you are current rating of the shaker, current rating of the amplifier is determined by the force rating, and the velocity range of the shaker is determines the voltage range of the amplifier. So these two are the designing factors. Now, apart from the amplifier shaker, we also have something called controller. This is the place where we input the spectrum, and the spectrum is again processed and then sent in the form of drive. For example, if I want a flat input, say from 10 to 1000 hertz, to be seen on the shaker top. So that means the shaker again is like a structural system. It has its own resonances. So those resonances, if I want this, will be amplifying and are reducing the input, and we will see as transfer function, that is the ratio of output to input in this case like this. But I want to see like this. So what controller does is it inverses. If wherever peak is there, it gives a valley. Wherever valley is there, it gives a peak. So that this drive is sent to the amplifier, and amplifier sends the signal in this form. But due to the shaker own transfer function, it will be manifested, and then we will be seeing the spectrum or say amplitude on the shaker like this actually, a flat spectrum or flat spectrum, that is 10 to 1000 hertz. So this is the purpose of the controller. That means it will manifest or it will control the transfer function of the all associated equipments mounted on the shaker, and input as desired onto the unit under test. There are various vibration controllers nowadays available in the market. Now, apart from this, we need some instrumentation systems, like you need accelerometers, you need data recorders, you need cables. Basic accelerometers, initially what were used was piezoelectric accelerometers. Initially there were charge type accelerometers. Nowadays all systems are being used as voltage type, or what we call ICT type, integrated circuitry for piezoelectronic type. Why charge type were initially used was they were very easy to design, and then initially only compression type charge amplifiers were charge accelerometers were there. Nowadays shear type charge accelerometers converted into voltage type are predominantly used. And apart from this, why we use accelerometers? Because the bandwidth of the accelerometers are very high. It can sense very low vibration also, and it has wide ranges. It can be mounted on any places. It is very small, so it has many advantages compared to displacement and velocity measurement systems. That is why accelerometers are widely used, and they are categorized like uniaxial, means sensing motion in one direction, or triaxial, sensing motion in three axes, and so on. Again, the piezoelectric, when we say, the frequency response is typically from few hertz to kilohertz, and it is not DC, because piezoelectric effect itself says whenever there is a dynamic motion, an output is seen. So if you want to measure a DC response also, then we have to go for piezo capacitive or piezo resistive kind of accelerometers, and not piezoelectric. Piezoelectric sensors have to be mounted on the surface. So there are different mounting techniques possible, with adhesive, with some magnetic based, or stud mounted. Out of all, stud mounting will give you the best mounted frequency. The mounted frequency means this crystal will have, or the accelerometer will have one resonance. You are supposed to use in 5 to 10% of the mounted resonance frequency. So your bandwidth, or the usage of the accelerometer resonance bandwidth, comes down if you are using adhesive, and so on with simple probe like things. So generally we are using adhesive type, which is intermediate, or say fifth, very less to very close to stud mounting. Stud mounting is most preferred, but most of the locations you will not be able to fix the stud. So in those cases you can use adhesive. Again, the amplitude of vibration or shock again will determine the condition. Like if you are crossing 100 G or so, you are definitely bound to use stud mounting. So adhesive and stud mounting are predominantly used, and like in some modal analysis, or in some cases where you are not allowed to use even adhesive or stud, you can use magnet based mounting systems. But then your resonance comes down, so then you are supposed to use the bandwidth of the accelerometer within 5% of its resonance, or 5 to 10%. So appropriately you should choose actually. And then for vibration testing, I have told one electrodynamic shaker. Few typical representative photographs I am giving. This is typically says 16 ton, or say 1,60,000 Newton shaker, where apart from the shaker, we have to use some associated equipments, what we call as head expander, that is expanding the base of the shaker to some other shapers. That is because you will have a large surface items. You can't have one shaker for say 1000 mm, another shaker for 2000 mm. So in those cases we use associated equipment which will expand from 100,000 to 2000, and we can mount the system here and control appropriately. Likewise, the shakers are also allowed to rotate 90 degrees to perform vibration in another axis. Typically all aerospace systems are supposed to be vibrated or tested in three axes. So one axis is done in this mode, what we call vertical axis, and when you rotate it and put onto other system called slip table or other accessories, and then you mount the system here and you generate other two axes. Once by putting here, and next you have to rotate the system or rotate some other fixture or so. This is how vibration is performed in three axes for for most of the aerospace systems. Now, apart from vibration, I was also telling about shock and bump. There is very little difference between shock and bump. Bump is a continuous shock. Shock is a relatively very transient event of high magnitude and low duration. Typical pulse of shock is like milliseconds and microseconds, and below that only. A typical frequency range for a mechanical shock is up to 500 hertz. Mechanical shock is again classified into what is called as classical shock and pyroshock. Whatever we are simulating in laboratory, we call it as classical shock, and it is up to 500 hertz only, or say a few milliseconds. It can be like say 40G 6 milliseconds, 40G 11 milliseconds of kind of shock can be simulated with shock machines which are basically hydraulic type or pneumatic type. But there is another shock, what we call as pyroshock, which is very severe. This is due to some charge ignition and other igniter bolts or so. This pyroshock is classified into three types, basically far field, midfield, and near field. Near field shock can go up to 100 kilowatts with say amplitude of even 1 lakh G. These kind of shocks cannot be simulated by laboratory, so they have to be actually simulated by firing the actual systems and and testing. So but this repetitiveness is not attained in these kind of systems. So researchers have come up with the midfield and very far field shocks, which are like up to 10,000 hertz and say 10,000 G, which can be simulated by mechanical means, and you can test number of times. But if you want to simulate pyroshock of near field, then definitely we have to use the actual system and then simulate. So this shock also causes a lot of failures in aerospace. So this again has to be simulated and tested for every equipment. Similarly, whenever you have a curve or turn, even in a bus you would have felt many times, you are pulled to one side, either inside toward the center or outside. That is what we call as acceleration. Whenever speeding object is taking a curve or maneuver, you get an acceleration. So this in actual flight, they are going with very supersonic speeds. You get lot of accelerations inward. Like say we say typical numbers are like 10G, 20G acceleration kind of numbers. These have lot of effect on again electronic components, and also structures like bolts and other things fail. So these have to be simulated. These are simulated on some systems called centrifuge. Here, a center one kind of boom is taken. Like it is like a rod with some center direct driven motor, and it is rotated. One end you are putting unit, other end you are putting a counterbalance mass, and acceleration is like proportional to r omega square r. It is proportional to its angular velocity and radius at which you are putting it. So these systems have to be tested, and if there is any failure, it has to be corrected. We have acoustic vibration systems, which vibration testing chambers. This is all aerospace. They get acoustic levels are 20 dB and above. They go high as 160 dB, and like typical man we cannot withstand 120 dB even for 1 minute, but these systems like PCBs and connectors, they have to withstand 160 dB, 170. We have what we call as vibration chamber. We are able to simulate up to 160 dB. We have seen number of failures during the lift off due to the very high propulsion exhaust gases, and then high aerodynamic oscillations. Sound induced vibrations are coming, and they have effect on these systems like air intake oscillation systems, and there's some surfaces what we call as fin systems. They oscillate them. Then if they are getting oscillated, we have a control loss actually, and some cracking of PCBs and some wires issues, and there are any optical elements which are very sensitive to the vibration, and they also have some damage. So the systems have to be also tested for acoustic. Typically the acoustic environment will be given in terms of pressure versus frequency. Typical spectrum is like 150 dB or so for say 10 seconds to 15 seconds. And having seen different environments like vibration, sine, bump, and acceleration, I would like to brief upon recent advances. Like we are talking all these electrodynamic shakers, which are above 2000, 1990s, 1945 mechanical shakers started up to 2000. All the electrodynamic shakers are able to do all the things. Technology is saturated, but there have many advances have come with respect to testing technologies. That is why these advances have come is the aerospace and defense systems in actual flight, they get all three vibrations or say all three axis vibration at a time. So to simulate that vibrations, or to simulate more realistically the vibrations that are felt for long systems, different techniques have come, what we call as MIMO systems or multi-axis test. Whatever we have been explained up to now is like single exciter, means one shaker in single axis, what we call. So we can do single input single output, or multiple input single output, or in these systems we are only controlling amplitude. This is what like you typical system shaker is looking like. You will have either horizontal or vertical, and you will be able to control. But with the recent advances, we have multiple exciters, single axis. What it means is you have multiple shakers. You have a very lengthy systems. You can excite it at 2 points and then get a very realistic environment. Or you have a multiple exciter, multiple axis. You have couple 3 to 4 systems or 6 systems in 6 axis or 3 axis, and you put the system and excite in all 3 axes simultaneously. So there are different techniques like single input, multiple output, multiple input, multiple output. This is what is these systems. In these systems, apart from only amplitude, like I was telling 5G, 2G in different frequency ranges, you need to control phase and coherence, because the excitation of one axis should not affect other axis, or this axis excitation should not affect in another cross axis. So for that we need to control phase and coherence. These are even achieved even in aerospace industries very late, but in other automobile industries it has been done from very long decades before. I will explain the reason why. So why we are doing multi-axis is we are exciting the input excitation energy in 3 axes simultaneously. This is more realistic. See, application of multiple exciters providing dynamic input to the test item in a way requires more than a single vector for complete description of the excitation and measurements. It is more realistic and imposes synergetic effect in all 3 axes simultaneously. But why this was single axis was followed in aerospace industry up to now and not before? Because earlier, say up to 2008, there was no standard. In 2008, one standard has come for multi-axis. But whereas in automobile industry, right from 1970s, they are following with 6-axis motion simulator, 4-axis motion simulator, 2-axis motion simulator, due to available test equipments and test standards. Why test equipments are available for automobile was, the reason was their requirement of frequency range was 500 hertz. So for that test equipments were available, but for aerospace it was not available. What was the system which was not available was the coupler, what we call as spherical couplers, which needs to simulate this 2000 hertz requirement, was not available actually. Oh, multi-axis, this I already dwelt upon. So what the difference between single axis and multi-axis system, it lies in the controller basically. Controller in single axis, what we are doing is this shaker, where controller generates a drive and it gives to shaker and the system is felt, and this is again in closed lab. Whereas in multi-axis system, you have number of shakers. This is driving the system under test. The controller gives drives simultaneously to all this, and again takes the feedback and gives to this. So here we are generating not only amplitude, phase, coherence, and it is very complex mathematical technique to generate multi-axis vibration system. So a typical example I am showing here. You can couple 2 shakers like this and put like this at a far off distance and test the entire system in one go, or couple side by side and so on actually. Or you can do like this also, make them up and then do like this. These are widely followed by NASA and many other defense agencies actually. Or you can couple all 3 axes at a time and do. Apart from this, sometimes you have to transport the entire system to from one place to another place. This involves a typical road scenarios. It can be, if you are transporting by road, it can be a cross country road, a road with high sand, a road with muddy road with a good track, and so on. So all these are possible to be simulated and then tested. For example, there are different tracks which are available actually. Test standards are available, and also test tracks are available, on which what we call something like Belgian paved track or mud track, or that equipments can be put in some simulation systems and then taken into these things and then be tested. So these are all what we call as transportation system of large systems. The standards are available, and also testing facilities are available. Now we have seen different dynamic tests. To do basic vibration test, I was mentioning some associated equipments are required, like what we call as head expanders, slip tables, and fixtures. Fixtures I will dwell upon briefly. Fixture, what is a fixture? Basically, it is a vibration and shock fixture. It is an intermediate element between the shaker and the unit under test. On the fixture, you will mount the test item. So what it has to be doing is it has to transmit the energy from the shaker and transmit it to the unit under test. That means rigid transmission is required. Fixture should not alter the or increase or decrease the motion that is given to it to the unit under test. But most of the times it is not so. So that is why how to simulate or how to design a fixture I will just dwell upon. So the fixture, other requirements of fixture is it should simulate field mounting condition. That is what we call service mounting condition. Suppose if a unit is mounted with two bolts in actual service, we have to mount same service mounting condition. We have to simulate, and fixture should also facilitate testing in multiple axes if required. Basic requirements I am putting here. First, it has to simulate service mounting condition. It has to do faithful transmission of the input without distorting the levels. It should be the integral part of the table. The other requirements are it should have very high natural frequency and high damping. Why high natural frequency is it should transmit if there is a natural resonance within the operating range, it will amplify or it will decay. And damping is required because we need to control the input, and if there are resonances, only damping can help to reduce the amplification ratio. A typical systems I am just putting here, how like they can be like this big L fixtures with channel type fixtures, big systems, or it can be round fixtures as solid stocks, we can make it, or some kind of systems with as a entire systems we can make it. In all of these, what are the inputs we need is what are the test specifications, what is the static weight of the systems, and what are the number of test axes and test specifications. I was mentioning about damping. Fixture damping is required high. Why? Because if fixture damping is high, for example, damping decays the input very small time. So if damping is high, for example, if damping is of say 1%, it is decaying like this. If it is say 5%, it is decaying very fast. Means time taken to reduce from say particular amplitude to particular amplitude is more in the high damped systems. We need these characteristics of the fixture because we are going to control the vibration, right? And generally we have to operate, a fixture has to be operated in this zone, because if you are operating in this resonance zone, you will be getting very high amplification, and beyond root 2 of its natural frequency you will be losing energy. So typical transmission ratio of the natural frequency, if it is here, we will try to see that fixture is operated in this. But sometimes it is not possible. So suppose you have a 2000 hertz bandwidth, it is not possible to design a fixture up to 2000 hertz. Then you have to see that number of resonances are minimum and damping is helping you. Different types of fixtures I am just putting for a visualization purpose. Sometimes fixture we should not have welding here, so that you should have either full welding or patch welding is not possible, and number of bolts are less. These are all not allowed actually, and you should not use lengthy screws. And you should not use number of plates, interface plates to check item, because you don't have proper mounting this thing. You should not use clamping for up to 2000 hertz, because this will not transmit the vibration. No. Having seen the vibration environments and how to simulate, most of the times we are feeling the vibration response may be more in actual flight condition. So let us see how to reduce unwanted vibration response. The philosophy that we follow, what we call vibration response control philosophy, is like this. We have basic source to system, that is excitation is given by the source. System is manifesting, it may amplify or decrease, and you are getting response. For aerospace, most of the times excitation is from the source, means like aerodynamic or propulsion or other sources, which we cannot modify. Most of the times it is not possible. So then what we have to do, we have to either modify this path from the source to system, what we call as a transmission path. That is like, for example, use an isolator. And system, basically the unit under test, you can modify its structure, like chassis, or its weight mounted, or increase number of bolts, or totally redesign the system. That is what we call system modification. Or if you can do an active vibration control, we can get the response and send an anti-aliasing or anti-signal and see that response is mitigated or reduced. But this is mostly in vibration, active vibration control, it is used only for a very low frequency. Like for example, International Space Satellite System has one active vibration control of up to 4 to 10 hertz. This is generally not possible in aerospace application. So now we are left out with modifying the isolation, modifying the transmission path or modifying the system. I'll just give few examples where we have done source isolation and where we have done system modification, because excitation or reduction is not possible, but in other industries, yes, excitation or reduction can be possible. For example, automobile industry is there. If you are in engine to input some other chassis, it is coming, we can modify the chassis or change the engine transmission path. So while we need to control the input vibration or say response vibration, we need to understand this. Where is the originating source? What are the frequency content and amplitude of that vibrations input? And also how is the system dynamic characters and what is the path of transmission? If we know all of these, we can choose the appropriate philosophy to reduce. For example, if it is easy to isolate the path of transmission, we can use isolator. If it is somewhat not possible to have some transmission path isolators, we will use system dynamic parameters to change it. And for this, we need to know what are the frequency content of the vibration input or say whatever is the source and its amplitude. Modifying the source example I'm giving, though it is not possible in our industry, it is like you can do a proper balancing of inertia forces. If it is a sloshing of liquid, we can use perforated baffles, smoothing of fluid flows, using multiple number of smaller jets instead of bigger one, avoid vortex shedding, and helical spoilers, using helical spoilers. Uh, but for us it is not possible. We have done one modifying the system where we had one system what we call sensor package, which is very sensitive to vibration. It has some interface element like this, what we call as interface bracket. It was made of magnesium alloy, and it had some shape as it is shown here. There are this system is going to be mounted at 4 locations here, and it is going to be attached here also and here also. We had a differential input at this point and also at this point. I have listed here for a given input, and we were getting as high as like 85 GRMS for input of 0.404 at this point, and other point we were getting 35. If you see the difference between 85 and 35, so we were having around difference of 58 GRMS for 0.04, which means this is going up or down, and this is also not going in the same fashion. So that is again called differential input. For sensors, it is very dangerous and detrimental. So the sensor was not passing, and so what we did, we understood what are the frequencies and what is this structure is looking like, and we have used cross section damping. Like we have studied from literature what are the different cross sections and how their dampings are there. For example, I cross section is having more structural rigidity and also damping is more. So we used this I section to change from one end to another end, and then we have improved the configuration and tested. So what modification we did is some small pockets have changed. We have introduced I cross section and wedge shape for long beam. And what we achieved is amplification reduction was more than 50%, differential input reduced, and sensor errors are much less now. For example, after the test, you can see for 0.04, the differential input has come to 1.7, which was earlier like 58 GRMS. So this helped us, like small understanding of the frequency component and where what is affecting can easily be changed. And similarly, another sensor sensitive unit, which when we were subjecting to vibration input, we were getting very high vibration input. That is, amplification ratio was around 16 times. So we understood what was the issue, and we had seen that the system was very close to having a resonance around 2000. So we thought if we can shift this beyond 2000 by increasing the number of screws, this will come down. So we have increased the number of bolts and then reduced the amplification ratio, and then ratio of transmission was from 16 times to 1.7 times. This is how the system was protected. Apart from this, where system is not possible to be modified, you can do a path transmission modification. That is by introducing vibration isolator. What is an isolator? Isolator is an resilient element. What it does is it absorbs the energy and decays it over a small longer period of time. So thereby decays it slowly. So the zone of isolation should be beyond root 2 times the natural frequency, and so this should be the isolation zone. For a typical transmissibility curve versus frequency I am showing here, this will be the amplification zone, and we should use the isolation zone of the isolator in this period. For a few example of different types of isolator what we are using are shown here. There can be like this elastomeric isolators, metallic isolators, pneumatic isolators, hydraulic isolators. Different environments, different isolators are used. For example, if you want to use broadband range of isolation, we can use this. While selecting isolator, we need to be very careful. In the initial slide, I have shown one power PC which was about to be failed. That requirement there, we have solved that problem by using isolator. So to select an isolator, what you need to do is you have to identify what is the kind of environment or disturbance that is coming, what is the static load, so what is the frequency range of operation, and what are the other environments and ambient environments. If you understand this, if you can choose proper isolator, it is a very good method of solving the vibration problems. If the space that is the motion displacement is available, sometimes a poorly designed isolation system is almost equivalent to not having isolator at all, and it can even worst also. A typical example I'm showing a system where we had around this 25.75 GRMS response by using isolation. This peak is reduced, and then after isolation 90 Hertz is the isolator frequency. After that, we can see a complete cutoff of the input actually. This is how we can use isolators. And sometimes I was telling poorly used isolators are bad. For example, if you are using number of isolators in a system, like you have to use say 4 mounting points are there, you have to use 4, then you have to use them dynamically matched isolator. What we mean is the natural frequencies of all 4 isolators are very close, then it is good. Suppose if you don't use the dynamically matched isolators, then you will have a more problem actually. So one such case where we have used dynamically isolator, input is same but response you can see it has amplified, and in other case where we have used dynamically one, we have very less after isolation response. So this again same thing I was telling, isolation selection is very crucial and critical. You have to select them properly, and number of isolators when you are using, you have to use dynamically matched isolators. Apart from this, sometimes we have used damping techniques to reduce the input. For example, I was referring to something called head expander, where we need to increase the mounting surface, what we call expanding the head, so it is head expander. In such cases, when we were controlling the input, we were not able to control one odd 1000 hertz, its resonance of the expander was coming. To reduce this peak, we have used polyurethane foam filled in the cavities present here, and then we were able to control actually. So such damping techniques also can be used to control the vibration response wherever space is available and it is permitted. And sometimes I'm also showing some other examples of solid state recorder of one system where due to the vibration it failed actually. It was a long duration vibration. It failed due to the bolts have failed. There was a problem with the fixture. They have used very bad fixture of very fragile sections. Due to this, actually unit has failed actually. So the next care was taken that fixture was designed properly, and so the system also did not have any problem. And this is how, so even a badly designed fixture can affect the unit performance also, and also the fail the system also. So while doing a test, it is very crucial or critical. You should take care of your fixtures, test setup, test specifications, and other associated equipments also, so that they are not harming your test unit under test, and they are actually fit for the purpose. Now, having seen the vibration testing philosophy and also reduction methods, and suppose we are doing test initial stage of the project or the initial stage of the development of any system, we don't have test specifications. We will go by some standards or some other techniques. So once system is flown or some system is realized, you can do some measurements or you can collect some data. Once the measured data or collected data is available, now how do you convert them into test specifications which can be used in the ground testing for subsequent systems? So I will be dwelling upon this test specification developments. Basically, specifications are established at the beginning of the project for product design and are used during the test to show that the product meets the requirement. concerning the resistance to the environment. But specifications are specified for its different life cycle during, like it can be random vibration, mechanical shock, and so on. Actually, if you see the general life cycle of any systems, basically you have to do first analysis of the conditions of use. Means if you want to simulate or if you want to derive the specifications, what you have to do? First you have to know the life cycle of the product. So you have to use the analysis of the conditions of the use. You collect all the environmental data of that system and then segregate them as per the severity and apply some uncertainty factor and reduce them into the test time, and also by using the whether they are qualified for vibration, shock, that is appropriate damage criteria, you can be able to derive a test specification. So now I will tell some steps in how to derive the specification determination. Like for example, you need to know the analysis of the life cycle profile. You have to collect the data and convert the data into some different environments, and for each environment you have to establish a test program. A typical analysis of the life cycle means what are the environments it is going to be subjected, right? It's from design, production, and also use actually. So all the environments have to be listed and then all of them have to be subdivided into subcategories. Sample life cycle of a satellite I'm giving here. See, it can be initially there are there are two stages of its rockets. That means S1 and S2 rocket I'm calling stage 1 and stage 2. It can be handled in normal floor shop, or it can be transported. It can be air transported. It can be sea transported also. Now after all assembling, it can be actually used in flight. So there will be first stage ignition. You will have vibration shock here. You can have first stage propulsion, again second stage ignition, second stage propulsion. Like this you will have different environments. Each of these environments, whether it is qualified for vibration, shock, what environment, and what are the data, that we have to categorize and keep it. Now after deriving the different environments, second stage is determination of the real environment data associated with each situation. This has to be converted into test specifications. Like for example, if it is a shock, we convert them into SRS. If it is a vibration, we call them into power spectral density for studies and random vibrations. Now after you know the test methods, like it is shock, vibration, you have to derive the test specifications, and that test specification should be possible to simulate, or it should represent the actual damage of the measured data, and it should be simulated in the laboratory, and you should also see some uncertainty factor. If you want to put, you can put it. And suppose if it is a vibration, we are simulating something called vibration response spectrum. What is vibration response spectrum? I will explain with the example here. See, if any input is given, a multi-degree of freedom system is arranged into number of single degree of freedom systems with increasing natural frequency, and its input is given at its base, and each system will have its resonance, and it will have peak at one point. So that peak, that means all natural frequencies plotted versus its peak, if you plot, that is called vibration response spectrum. The input, why we are using vibration response spectrum is, in actual flight, if you get the data and directly you put an envelope of that and then do it, you are going to over test it. So that is what we call as traditional method. Instead of that, you convert into something called vibration response spectrum method and then use it. You will be having better advantage. For example, you have got some data like this measured data. You can see there is a peak here, there is a different, it is not like simple steady state or transient state, both are available. So you have to convert this data into steady state and transient data. Typically, for example, I have segregated into different events of say time cycle of 1250 to 1500 seconds, 1785 to 1800 seconds, like this different time events. And in each time events, I will get a steady state data and analyze them and come to some PSD data and envelope of all steady state data and get one other envelope actually for 140. Now this envelope will be given converted into VRS form actually. That will be given into the way I have told multi-degree of freedom systems like VRS system. and we will arrive at VRS envelope. This envelope will be again used to determine a test spectrum. For example, the envelope of the all this green is shown as envelope of all tested or measured data, and this blue color is what we have derived through VRS. We can see this blue color is not enveloping the peak, but still damage potential of this blue and this is same. So this is what is tradition is followed nowadays instead of traditional peak actually. And this is more advantageous. Just to show, suppose if you are using VRS and we using traditional, how they are showing, I'm showing here. This is a typical spectrum what is measured, and traditional method will envelop all peaks only, but VRS will envelop at some points, but VRS is more appropriate, and that is not over testing also, not under testing also. This method should be used for all flight systems. Similarly, if it is a shock, we come something called shock response spectrum. This shock response spectrum is used in many of the industries, like I have put it here. Why we use this? Because all this aerospace and military components are subjected to shock environment. To explain it again, I'll explain with some small. Suppose you have some, again, like vibration spectrum, it is derived or it is segregated into number of single degree of freedom systems, and now we will input some input shock to this. Suppose you can see how each system responds. One system may respond more, one system may respond high. So whatever at its natural frequency, whatever the amplitude of the system is plotted versus its amplitude at the natural frequency is plotted. So that if you plot, you get a shock response spectrum. So this tells you, for example, a field shock is like this. This has to be converted into SRS form, and this SRS plots will be given from the SRS plot. We will derive the what input we can derive in the field, so that correct damage input is given to the system. And a typical I have shown once thing is here. We have derived as 53G 1.8 milliseconds. Half sign is enough for simulating this kind of response on the systems. Why? Because we have seen, as I have shown here, if I input some, say here I am inputting 1G 1 second half sign pulse, we can see different amplitudes will have different. In this, appropriate input can be chosen to simulate onto the system. This is how a field shock is converted into laboratory test standard actually. Yeah, thank you. This is how we have to test different systems by converting a measured data into ground or laboratory test specifications. So with this, I will close my session. Thank you. Any questions, doubt, you can ask me.
Yes, participants, any questions, sir, from your side?
Hello, sir. Chandra Kumar.
Yes, sir.
Yeah, thanks for the nice illustration, sir. Hello.
Yes. Yes, sir.
Yeah.
Thank you. Please go on.
One or two queries, sir. Sir, in the transmittability curve you showed, you are going for the worst case condition, right? During testing.
Yeah. Transmissibility, why I have shown was, for example, isolator, if you have to use, no, you have to use in the beyond root 2 hertz, omega n into root 2 omega or 1.414 omega. For example, our specification may be up to 2000 hertz. Example, say, if isolator is at 100 hertz, that means I should use only from 141.4 hertz, but that is not possible most of the times. So, for example, I'm showing again, you have to use in this zone only, isolation zone. If you want to reduce the input is suppose 1, beyond root 2 times its natural frequency only, input is reduced. But if you are using isolator, no, you will have to face a small zone where it will be amplifying. So that zone, you have to control it by damping. That's what I wanted to say.
Okay, sir. And also, sir, automobile standards you spoke about, is it similar to MIL standards, sir?
No. There are different automobile. The 810G, and I was only telling with aerospace. There are number of automobile standards. There are available like that, but frequency is up to 500 hertz only.
Okay, sir. Thank you, sir. And can you suggest any reference material so
for
that we
automobile?
can?
For automobile? or
In
any other?
general, sir,
General.
general studies on vibration
Sir,
testing.
actually, to be frank, there are no books available for this, but I will tell you one you can note down. Wayne Tustin, Wayne, Wayne Tustin, Tustin. Wayne Tustin, you can check in the net, sir. It is available. Some philosophy, some books, some reference is available.
Okay, sir. Thank you very much, sir.
Yes, sir. Thank you.
Sir, this is I'm Sir Bhanu Prasad, who has been I'm interacting with you quite
Yes, sir.
for quite
Yes,
some
sir.
time, sir. Sir,
Yes, sir.
I have one specific doubt actually. What the dynamic matching of isolators mean?
Yeah, what we mean is, suppose if you are using, suppose say a rectangular box, suppose you want to isolate it, you will have four corners. Generally, they will have four mounting. Assume we have four mounting points. If you select four isolators, now you are not checked. Simply manufacturer has given you, you are using four isolators. Normally what happens, isolated natural frequency may vary within plus minus 0.5 hertz or so. That is okay. But if it is varying by more than 1 or 2 hertz, say one isolator frequency is 20 hertz, other is 22 hertz, other is 26 hertz, like that, suppose, then what happens, your system may be isolating in one axis, but in other cross axis you will be seeing motion which is more than the required actually.
Yes, yes.
That is what we mean. Dynamically matching means you should do a test before. For every isolator will come with its rated load and natural frequency. For the given rated load, you have to check beforehand and see that all natural frequencies are very close. Like I was saying, within plus minus 0.5 hertz.
Yes.
If you don't do that, you will have a problem.
Okay, sir.
But at least for us, we are, suppose I am getting 1,000 isolators. I am screening all 1,000 isolators to know the natural frequencies and then segregating them, grouping them actually.
Okay.
It is a time consuming process, but you have to do. There is no other way.
Yes, sir. Yes.
Yes.
And sir, another thing actually, when we talk about the control of vibrations, what specifically
Yes.
are we controlling? Is it the frequency or the amplitude or both?
Amplitude, sir. Frequency, we are not changing. Amplitude only. At
We will
damping, why
not
we are
change.
talking about
Even in the case
frequency?
of isolation also.
Isolation, the damped natural frequency is very small, like omega n,
Sir.
omega d is into 1 minus zeta square, omega n into. So there will be small change. Yes, sir. If it is say 100 hertz, it may come to 98.
Okay, sir.
But the amplitude ratio, transmissibility ratio will come down.
Okay. Okay.
If you are modifying the system, yes, then you have to play with natural frequency, sir.
Okay,
If
sir.
you are modifying the system, you have to play with the natural frequency.
Uh-huh.
If you are modifying the path, transmission path, then you have to do play with the damping.
Okay, sir. Okay, sir. Thank you, sir.
One more, sir. One more. See, if the natural frequency of the system in initially without isolator is some X, suppose. With
Sir.
isolator, it will come down. It will be the isolator natural frequency now, not the system natural frequency.
Okay, sir. And any more questions from the participants?
One man has asked like what is the effective vibration of subsystems and entire system?
Sir, one gentleman have posed this question in the message box. Actually, what
Yes.
is the effect of vibration on subsystems it's a vibration of subsystems on entire system?
Yeah. What we mean is, suppose you a bigger system is what we call section or say bigger system. It is a combination of many subsystems.
Okay.
So now at a system level, if you are testing, the input will go from the system, then to the interface brackets or say to the system subsystem. If subsystem is amplifying more, suppose subsystem is violating or oscillating at some natural frequency or say at its resonance, then that is going to have back effect on the other components also, surrounding components also. That is the effect of subsystem on section. For example, aircraft is there, sir. Fin is there. If you are having flutter, flutter will come from the fin, but fin can make the entire aircraft collapse.
Okay.
That is a subsystem to system.
Yes. Yes. Any other audience? Any other participants? Any queries from your side, sir?
You can unmute and
Yes, you can unmute your systems and you can ask if you have any questions. Okay, it seems there are no questions from the audience,
Yes.
sir. Sir,
Yes.
so now it is time that we conclude the session, sir. Sir,
Yes.
and
do we have any such a case where I thought within the ISO is zero?
yes, sir. So, one doubt was posed here, sir, and that is,
Yes.
do we have any uh, such case of a subsystem influence on the entire system where the sorry,
Isolated.
Yes. Yes.
okay,
Yes. Yes.
where
Yes.
the
We have.
isolator within the isolator is used? Do we have any such case where
Yeah. Stage.
isolator within the isolator is used?
Yes. I mean, not like that. A stage-wise isolator, like two stage, three stage. Yes, we are using.
Ah, yes.
Like some systems, inside some sensors are there. They have isolator inside already, and because that isolation is not effective, so we are using another stage of isolation externally. We have isolate, that is like isolator inside another isolator.
Hmm.
Two stage and three stage are available, sir. Number of
Okay,
cases,
sir.
two stage. When the efficiency of the there is isolator efficiency for a given input, if it is not sufficient, we use. I will tell you another case also. Suppose you are transporting some system. All our vehicles, this lorries and others, they have a suspension system of three heads. This
Yes.
hydraulic or pneumatic and other air also. So if you when we transport our bigger systems, we put one more stage of isolation, wire mounts we put and then put it. So that is two stage isolation. Already it is 3 hertz. So we will use less than 3 hertz. But that time when you are using second stage isolation, you should be careful. So you should now use below or very low frequency isolation.
Okay. So
The care.
so it means, sir, the frequency of the primary isolator must be larger than that of the
Yes.
secondary
Second.
isolator. You mean to say, sir?
Yes. Yes.
Okay. Okay. So any more doubts from any more questions from the audience or the from the participants? Okay, sir. Thank you very much, sir. First of
Thank
all, Dr. Reddy garu, first of all, we have to thank you for accepting, our invitation and coming forward to give a deliberate lecture on vibration control on the very first, message that we have given to you long back, and
Yes.
we are very much thankful, Ben, for that, sir. And,
Yes.
and this is a wonderful lecture, and of course we all felt that it is a complete roundup of say vibration testing laboratory within this 1.5 hour span, sir. This is a really wonderful experience for all of us. And I mean, you have tested, I mean, you have educated us, you have enlightened us on the failure reasons of failure reasons, and the dynamic tests and the types that are and the types of dynamic tests, and the basics of vibrations and vibrating tests, and why these tests are performed specifically. You have given a wonderful explanation on that, sir. And you have given a nice demonstration on the failure due to vibrations. And you have you know uh, educated us on the sine and the random vibrations and the laboratory testing. And it is like, you have taken out as the basic testing philosophy, I mean, primarily. And it's a wonderful experience for all of us. And you talked about the various methods of the testing of vibrations. And last but not the least, this one, the test specification development, a very wonderful concept that you have given us as a part of your lecture, sir. So this is as a wonderful experience for all of us to have a practical touch on the vibrating test, say vibration testing, I mean vibration isolation, I mean phenomena. So Thank you very much, sir. Thank you very much for your time and effort that you have spared for us to enlighten us on this vibrating as a vibration test. Myself, Bhanu Prasad and Dr. Anjaneyulu, both of them.
Yes.
Uh, uh, Thank you very much on the behalf of
Yes.
the Department of Mechanical Engineering, Vasavi College of Engineering, sir. So once again, thank you very much, sir.
Yeah. Thank you, sir. Thank you, all the audience.
Yeah,
Shall I log out, sir?
yeah, yes, sir. Yes, sir. Yes, sir.
Thank you. Thank
Yes, sir. We will get back to you, sir.
you. Yeah, thank you.
Yeah, yes, sir. Yes. And
Thanks for
thank
the.
you all, audience, as a participants, for your time. And we will be sharing the feedback form to you shortly. Please, send us your valuable feedback. Okay. Okay. Thank you. Thank you, one and all.
Okay, thank you all. You can use the feedback either here or in the WhatsApp group. Please fill it, sir.